Good morning, and thanks for attending this presentation. We will focus on the different methods of electric wiring on machinery and industrial plants. In particular, we will concentrate on the main differences between the methods used in Europe and those used in North America due to the different regulation. My name is Massimo Ceolaro, and I'm in charge of R&D in Tekima. This presentation is divided in two slots. The first, followed by me, and the second by my colleague, engineer Alessandro Giovannini, who is the technical director in Tekima. Well, now let's see what usually happens in a company when a new contract comes from North America. What are the questions that are normally asked? What is the destination market? What is the scope of the contract? What are the standards? And last, what are the required certification marks? Therefore, first question, as we well know, from a rules point of view, when we talk about North America, we have to distinguish between United States and Canada. Second question, what is the scope of the contract? The North American standards contain a strict separation between the different wiring methods, depending on whether they are industrial control panels, industrial machines, and electrical installation in a building. This permits to analyze three different levels of wiring: plants, machinery, and control panels. As you can see on this slide, for each one of these three levels, we can have a different specific standard depending on the issues addressed. For more details on this different standard, you can refer to the presentation by C&D Consulting, which is a partner on this symposium. As we mentioned before, these are the standards for the first level, electrical installation. The most important document that we have to consider is the NEC NFPA 70 National Electric Code. Second level, equipment. The most important document to consider for this level, which is most closely to our job, it concerns machinery, ANSI NFPA 79 industrial machinery. Last level, control panels. In this case, the master document to consider is ANSI UL 508A industrial control panels. As we mentioned before, when talk about North America, from a regulatory point of view, we must necessarily distinguish between United States and Canada. For the first level, these are the two main, let me say, book for the United States and Canada, respectively, NFPA 70, National Electric Code for USA, and C22.1 CE code for Canada. Same things also in the second level. These are the two reference documents, respectively, from United States NFPA 79, Electrical Standard for Industrial Machinery, and for Canada, C22.2, number 301. Finally, let's see what happened in the third level, industrial panel. In the third level, we have one main document for United States, UL 508A, and two standard for Canada, C22.2 number 286 and C22.2 number 14. As we have seen on the previous slides, depending on whether we are in Canada or United States, and depending on which type of wiring I'm making, first, second, or third level, I have to apply a significant number of different standards. If I have to sell the same machine or plant in Europe as well, I must also have to apply the CE standard that we already use today. At this point, the question that our customer often asks to us is, it is possible to design and build and control panel and machinery or industrial plant that meets the North American, Canadian, and European requirement at the same time? And this is the answer. The requirements are always different, so we can't. Up to now, we have seen which are the rules have to be applied in our machinery or plant. Right now, it is necessary to consider the products and related mandatory certification that will use over our machinery or plant. So it's therefore necessary to consider the different products to comply the standards seen up to now. When we combine the standard and product, it is necessary to consider a wide number of certification marks that certify the compliance of the products to the standard. First of all, it should be considered that depending on the geographical area in which I'm operating, there are different certification marks. For the USA, we see those on the left, you are recognized for Canada, recognized for US and Canada, and same for listed product. In the center of the slide, the most common in Canada, and on the right, the most common ones in Europe, like CE or VDE. We saw from the previous slides that there are two important types of product markings in North America: listed product and recognized product. Before choosing the right product for your application, it's essential to know the main differences between a listed product and recognized, and the compliance where they are allowed in a different application. In the Tekima technical manuals, you will find a short answer on the difference between the two markings. Another important issue concerning the markings is related to the market in which that mark is compliant with the standard. There is a lot of confusion in this. Again, this confusion is making a serious number of non-compliances. So it is therefore necessary to distinguish which is the certification body that has issued the certification and the mark in which that certification is valid. All the markings that you see in this column are acceptable for US market, even though they are released from a different certification body. Both in the top released from a US body, UL, and in the bottom from a Canadian body as CSA. So different marking from different body, but addressed to the same market. Same things for Canadian market. Are there any product marks that are compliant in both areas, USA and Canada? These are the main markings recognized in North America, but there is many other markings that meets the requirement, like QPS, ETL, FM approval, and MIT. What we have seen up to now is the main documents, the certification, and marks. Now, the object is to see which is the product and their own own certification in the different levels and in the different market. In USA, when I choose a wiring methods, I have to define which type of cable is needed. I have two options: AWM cables, recognized cable, or listed cable. So AWM is not allowed. In Canada, we have the same situation. AWM cable is not admitted. In Europe, CE markings and VDE and many other is for recognized as usable cable. For the machinery in USA, when I choose our wiring methods, again, I have to define which type of cable is needed. Two options in my pocket: AWM cable again, recognized cable, and listed cable. So both are admitted in this case. It's mandatory to observe that AWM cables could be used for industrial machinery. We have also to consider the installation because of the standard. In fact, I will consider some spatial evaluation depending on the application. Same situation in Canada. Moreover, for EU market, all the third-part certified cable is recognized as valid. Electrical panels. Same options for electrical panels. AWM cables and listed cable are both admitted in US and in Canada. In this case, without any special requirement. Again, for EU mark, all the third-party certified cable are recognized. How can I verify the certification of the cable and for which market is compliant? Are there any marking rules for the cable? Let's see. It's important to say that contrary to Europe, cable markings in USA and Canada are strictly regulated. Some indications are mandatory, while others are optional. Any additional requirement must, however, be tested if printed over the cable. This is an example of marking for Tekima cable. Trademark, size and number of conductor, voltage rating, temperature rating, wire type and file number if it's listed, AWM style and file number if it is recognized, certification mark. All of this is mandatory. The other one, like flame resistant, is optional. Sound resistant is optional too. Now, using the examples, we will see the main differences on the application. Let's focus on the USA and Canada requirements, leaving out at this stage the European requirements that we all know well today. Back again to the first level, plant. As we have seen before, two main standard National Electric Code for USA and Canadian Electric Code for Canada, where I can find the references of the wiring products that meets the requirement in the National Electric Code. On table 392.10a, there is a list of products that are compliant with the standards. Just for instance, electrical metallic tubing, EMT, flexible metal conduit, FMC, and tri-cable. In this example, you have to wire a panel to a machinery. In this case, you have to install the tri-cable in cable tray. And when you go out of the cable tray, tri-cables exposed run are needed. And in Canada, quite the same approach. In the CE code, you will find table 19, which is the list of products compliant with the standard. Some example for the cable is tri-cable TC or Tech 90 armored cable. For the same example we have seen before for US, here the wiring methods for Canada. Tri-cable in the cable tray and take 19 or tri-cable exposed run or other recognized cable but protected with a raceway. Second level, machinery. As we have mentioned it before, two main standards, NFPA 79 for USA and C22.1, C22.2, number 301 for Canada. What the norm says regarding the wiring methods. In the NFPA 79, in point 12.9, special cable and conductor, you can find all the answers. Just for instance, here we are on the machinery and we can use AWM cable with UL or CSA recognized markings in the cable tray, AWM cable between the cable tray and the equipment, but protected in the raceway. There is an exception. I can use AWM cables without any protection, just if it's followed and fixed over the structural part of the machine. What's happening in Canada? Same situation. AWM recognized cable in the cable tray, AWM cable in a raceways, unprotected AWM cable just if are following the surface of the machinery. And the end. In the control panels, again, one main standard, UL 508A for USA, and two standards, C22.1 and C22.2, number 286 for Canada. What is the requirement for cable inside the panels? Minimum temperature ratings 19 degree. Machine tool wire that is listed cable or AWM cable that is recognized cable for internal wiring. Same things for Canada, where the 19 Celsius rating is mandatory too. One important thing is to double check the temperature rating of the cable and the temperature rating of the associate component. What other components are required for wiring? We spoke about name as raceway or cable tray. Each one of these components is defined in the standard, and you can find all the references on it. Just for instance, at the point 3.3.76, you can find the definition regarding the raceway. Same thing for cable tray. Are there an exception? The standard considers, for example, the structural part of the machinery used as a system to convey the cables. This is a quick overview regarding the different type of raceways. On the left are rigid raceways. On the right part of the slide, the flexible products. On the descriptions, you can recognize the same name we mentioned on the slides before when we saw the list of wiring methods approved by the standards. As always, in the standard, you can find the exact definition of the product. And in that definition, you can see that the products need to be listed. So, recognized markings or CE mark are not allowed. An overview regarding the cable tray system. It's very similar or what we usually applied in Europe. Wire mesh, solid bottom, walkable, ventilating through. And again, in the standard, you can see that the products have to be listed. Recognized markings or CE mark are not allowed. Regarding the definition of other systems, they are considered as exception, and anyway, the standard considered this system as raceways. Do exist methods to size raceways and cable trays? How we can size the cables installed inside. For the raceways, the sizing methods is in the NFPA 79. For cable trays, the reference is always NFPA 70. Let's see some example.
First example, let's try to size a raceway type liquid tight flexible non-metallic conduit B, which contains 6 cables series 8110 tri-cable exposed run with 5 conductors 12 AWG size. The first step is to find the diameter of the cable. So if we look into the technical catalog of Tekima, we will see immediately what is the external diameter of the cable. In this case, a 5 conductors 12 AWG will be 14.3 millimeter. What is the percentage of cross-sectional area of the raceway that we can use for the cabling? According to the NFPA 79, we can reach up to 50% of the interior cross-sectional area. We don't have any limits in the length and any limits in the number of cables contained. Step 3. Calculate the minimum size of the raceway. To do that, we have to understand the total cross-sectional area occupied by the cables. For one cable, the cross-sectional area will be 160.5 square millimeter. That means that for 6 cables will be a total of 963 square millimeter. With a percentage of 50%, we can understand what will be the minimum internal area of the raceway that we have to look for. That means 963 divided by 0.5, which is 1926 square millimeter. We can now find the commercial size of the raceway based on the result obtained. The raceway that allow to reach at least 1926 square millimeter is a 2-inch raceway. That means a raceway with an external diameter of approximately 59.9 millimeter. As a second example, we will size the cable tray which contains the same cables that we have seen installed in the raceway in the example before. And let's consider a cable tray ventilated. As a first step, we have to find the external diameter as in the example before, which is again 14.3 millimeter. As a second step, we have to find the sizing method of the cable tray. And this process is completely different in respect to the raceway. The rules that we have to follow are contained in the Article Code 392 of the National Electrical Code NFPA 70. The National Electrical Code defines different methods of calculation depending on the type of cables contained, the size of the cable, and the type of cable tray selected. So it specifies the rule, for example, for ventilated ladder or wire mesh containing single core cables, is defining the rules for not ventilated cable trays containing multi-core mixed cables, but it also defines the rules for multi-core mixed cables installed in ventilated ladder or wire mesh cable trays. For this example, we are considering a multi-core cable 12 AWG installed in a ventilated cable tray. That means we have to follow the rules defined in the Article 392.22a1b that says the sum of the cross-sectional areas of all cables shall not exceed the maximum allowable cable fill area defined in the neck. Step 3. calculate the sum of the cross-sectional area of all cables. To do that, we have to calculate the cross-sectional area of a single cable and then multiply by the 6 cable contained. So as for the example 1, we have 963 square millimeter. Then we have to identify the maximum filling area of the cable tray. To do that, we have to look into column 1 of the table and look for the allowable filling area that can contain the cross-sectional area of the cables. In this case, 1500 square millimeter are enough to contain 963 square millimeter. This means that the width of the ventilated cable tray must be at least 50 millimeter. So let's find the product into the technical catalog of Tekima. The cable will be distributed in 2 layers, which means that the height of the cable tray has to be at least 35 millimeter, and the final solution will be a cable tray 35 millimeter height, 50 millimeter width. What is the most convenient system between the raceway and the cable tray? Based on what we have seen till now, the selection of the two solutions can be based on the geometry, of course, and on the installation method that we have to apply. But are the two solutions influencing the cable's performance? Let's see with 2 other examples. Example 3. Calculate the ampacity of the cable series 8110 tri-cable exposed run with 5 conductors 12 AWG sized installed in a raceway and working at 30 degrees Celsius ambient temperature. The maximum cable ampacity is calculated using the nominal ampacity of the cable adjusted by 2 factors which take into consideration the ambient temperature and the conductors grouping. First step, look for the ambient temperature correction factor. We are working at 30 degrees Celsius, which means that independently on the temperature rating of the cable, the factor is equal to 1. So we do not have any effect at 30 degrees. Step 2. Look at the correction factor depending on the number of conductors in the raceway. Based on the rules, the derating factor is depending on the total number of conductors carrying the current. In this case, we have 6 cables made of 5 conductors. The total amount of conductors carrying the current is 24, which means that the adjustment factor will be 0.45. Step 3. Find the nominal ampacity of the cable. Based on the temperature rating of the cable and the size, we can identify the nominal ampacity using the table contained in the standard. So for this cable, we have 30 amperes as nominal ampacity. Step 4. Calculate the maximum operating capacity. To do that, we have to apply the adjustment factor to the nominal ampacity of the cable. So we have 30 amperes multiplied by 1, that is the ambient temperature, the rating factor, multiplied by 0.45, that is the derating factor related to the conductor grouping. The result will be 13.5 amperes, which is the maximum operating ampacity of the 6 tri-cables installed in the raceway. With example 4, we will see what is the maximum ampacity of the 6 tri-cable installed not in the raceway, but now installed in the cable tray. The rules to follow in this case are defined into the NFPA 70 National Electrical Code. As before, we have to find out the ambient temperature correction factor. That will be 1 because the ambient temperature will be the same. Step 2. Look for the correction factor depending on the number of conductors in the cable tray. According to the NFPA 70, the adjustment factor will be limited to the number of current carrying conductors in the cable and not the number of conductors in the cable tray. So the adjustment factor that take into account the conductors grouping into the cable tray is completely different in respect to the adjustment factor for the conductors grouping used into the raceway. Considering this rule, the number of conductors carrying the current into the cable is 4, which means that the adjustment factor in this case will be 0.8. Step 3. Find the nominal ampacity of the cable. Again, using the table contained into the standard, we can find that for a 12 AWG cable with a 90-degree temperature rating, the nominal ampacity will be 30 amperes. So we can calculate the maximum operating ampacity of the cables installed in the cable tray, which is the nominal ampacity multiplied by the rating factors. 30 amperes multiplied by 1 multiplied by 0.8, which is the rating factor due to the conductors grouping. In this case, we have 24 amperes. So if we go back to the original question, what is the most convenient system, raceway or cable tray? The answer is related to the maximum performance that the systems allow to obtain with the cable. For the raceway, we can reach up to 13.5 amperes. With the cable tray, we can reach up to 24 amperes, so it's 77% more ampacity in respect to the raceway. If we want to reach the same operating ampacity in a raceway, we should move from a 5 conductors 12 AWG size to a 5 conductors 8 AWG size, which means that we have to size again the raceway, moving from a 2-inch to a bigger diameter. Till now we have seen how to size the raceway, how to size the cable tray, and how to calculate the maximum operating ampacity of the cables contained. But what is the method to size the cables? In the previous example, the size of the cable was already defined. Let's see in the final example how to understand the size of the cables according to a specific standard. In the example number 5, we will size again a tri-cable exposed run series 8110 made of 5 conductors operating at 20 amperes and 40 degrees Celsius ambient temperature. Standard reference is the NFPA 79 industrial machinery. The first step is to understand what is the rating factor for the ambient temperature. We are working at 40 degrees and the tri-cable that we have to size has a temperature rating of 90 degrees, which means that the rating factor for the ambient temperature in this case will be 0.91. The second step is to define the correction factor depending on the number of conductors, exactly like we have done in the previous examples. In this case, we have 4 conductors carrying the current, 1 is the ground, so in this case the correction factor will be 0.8. Step 3. Find the nominal ampacity of the cable. To understand the nominal ampacity of the cable, we have to divide the working ampacity of the cable by the derating factors. So we have 20 amperes divided by 0.91 and divided by 0.80, which gives 27.5 amperes. Looking the nominal ampacity of 27.5 amperes into the ampacity table contained into the standard for a temperature rating of 90 degrees, we find that the highest closest value will be 30 amperes, which correspond to a 12 AWG size. So the minimum required size of these conductors will be 12. Does it exist a faster way to size cables, raceway or cable trays? The answer is yes, using our SolveTech application. Does it exist a faster way to size cables, raceways and cable trays? The answer is yes, using our SolveTech web application. With SolveTech, it's possible to calculate the voltage drop, the maximum length, the maximum load and the size of the conductors, the diameter of the cable bundle, the dimension of the most suitable heat-shrinking tubing, the size of the raceways, or the size of the cable trays. SolveTech simplifies the work of the technical offices and designers by providing calculation methods based on the main standards and on the various regulatory editions. For more information, visit us at www.tekima.com or contact your Tekima experts right now at the Electrical Engineering Day 2021.